So I want to wrap up with something a little bit more practical. So, like I said, some of my collaborators are looking at this from a more practical perspective. So they're really not very impressed with my idealized assumptions. And in fact, I remember I generated this curve for a paper, and I showed it to them, and they said, okay, that's great, but it's totally unlike anything we're actually doing in practice. What the real problem looks like is this. So we, again, have our motor moving along here, except what it's supposed to do is it's supposed to pick stuff up, pick up cargoes from a loading zone, and deliver them to an unloading zone. So basically, the microtubule will swing around here, pick something up from the loading zone. That cargo will then attach to the microtubule, move over here to the unloading zone, where it gets dropped off. So if you like, this is kind of like nanoscale postal mail. So you're sitting over here with a letter. That letter is picked up by the letter carrier and is eventually dropped off at the addressee. So the question is, what are the achievable rates of that kind of a system? So again, I have my fancy simulator, and this is kind of what it looks like. The loading zone is over here, and the drop-off zone is over here. So this thing is red, so it hasn't picked anything up yet. It has to go all the way back over here in order to pick something up. We'll see that in a second. As soon as it gets there, it picks something up, and now it has to come all the way back to the unloading zone in order to drop it off. So this is like the letter carrier on his route. He's doing his route, doing his route, doing his route, until he picks something up from you, and then he has to go all the way back to the letter depot or wherever to drop it off. This is work in progress. Here's some of our early results. The interesting thing about this is that if you do it with Brownian motion, it seems like it should, Brownian motion should be better and faster, because in Brownian motion, okay, so if you want to talk about ludicrously stretched analogies, the Brownian motion solution is like tying things to helium balloons and letting them go. So there's no limit on, let's say, the amount of helium you have, so you can transmit an unlimited amount of information at once. It's just that its propagation is totally random. However, on the other hand, there's only one letter carrier that can come by and pick your stuff up. Now, what we would have expected is that Brownian motion should dominate. Now, it does over the long term. The x-axis here is the number of available packages that you have to deliver. Over the long term, this will eventually go to infinity. But if you only have a few packages available, this is with just one letter carrier, if you like. The motor-based propagation comes to a peak much earlier. So the takeaway message here is that the regularity of motor-based propagation seems to dominate. Here's some future questions for this. Quite apart from refining the models, I mean, there's lots of work to be done just in making things a little more refined in all of the techniques that I've talked about. But here are some sort of medium future questions for you. Firstly, geometry. So in a lab on chip, all I showed you, and all the results I showed you were for straight tubes. So let's say you have to go around a corner, or let's say you have fan in or fan out, or problems of that nature. Well, where does the geometry of the transmitter and the receiver come into the mutual information? Another more deeply mathematical and information theoretical question is what I call experimental information theory. So for these tubes, what we have to do is we have to simulate them until we get a first arrival time distribution. They're not available in closed form, and the only way we can get them is by simulation. So what are the mathematical tools we need when we can't even write down the probability density function? So we need things like ordering results. In other words, if I give you a PDF and another PDF, can you immediately say, without checking, whether one has higher mutual information than the other? Another thing we need to talk about confidence intervals, which we don't talk about a whole lot in mutual information. In other words, need to have some probability, some error bars on our information results. The third thing, and this goes back to the question earlier, is mutual information even the right thing to measure? So mutual information is fundamentally a concept of digital communications, and it's not obvious that digital communications are the right thing to do here. And so is there something else we can do? Should we be measuring things like, in fact, I'm not even sure what entropy is maybe detection the wrong issue? Should we be looking at estimation instead? Questions of that nature. So with that, I'll leave off with some acknowledgements. I'd like to acknowledge my collaborators, Satoshi Hayama and Yuki Muratani from NTT Docomo, Ravi Adbe and Sachin Kadur, Sachin formerly at the University of Toronto, now with UIUC, and my PhD student, Arima. And if you want to contact me, there are my various ways. You may have noticed my camera down there. I intend to post this lecture on my YouTube channel, so thank you very much.